Hello, I'm Cassius Puodzius. I'm a PhD candidate at INRIA Research Center and University of Rennes in France. I'll be presenting the research paper Accurate and Robust Malware Analysis through the Similarity of External Cause Dependency Graphs. In addition to me, this paper was written by Olivier Zendra, Annelie Heuser, and Lamine Noureddine. Here you can see the outline of the presentation. We start with a brief introduction to talk about motivation and present our research questions. Next, we revisit some principles of malware analysis that set the basis for this work. Then we present the external cause dependency graphs, or ECDGs, and also our evaluation. And finally, we present our conclusions. Over time, we have been seeing an ever-growing number of malware that are getting more and more complex. To cope with this problem, we need to rely on automation. In this paper, we address the backbone question, how to compute similarity of unknown programs with high accuracy while being friendly to search and clustering algorithms for malware analysis. This question is break down into these three research questions. 1. How to get more precise structural representation of programs with respect to the state of the art. 2. How to exploit these structural representation to define a similarity function that is friendly to binary code search and clustering schemes. 3. How to evaluate this similarity function knowing that establishing ground truth for malware analysis is an undecidable problem. Before tackling the core aim of the work, we revisit some principles related to malware research. First, we propose what we call primitives. It consists of basic building blocks that appear recurrently in malware research. This idea is borrowed from the cryptographic community and consists of focusing on the functionality needed when building a malware analysis framework, leaving aside details of implementation. Besides defining with precision the vocabulary used in this work, the advantage is to facilitate the reuse and combination of different works in our community. Here you can see all the primitives that we propose. The main one for the remainder of this work is the code similarity. It is defined as a function that given two samples outputs a value between 0 and 1, where 0 means that the samples are totally different, whereas 1 means that they are totally similar. Please refer to the paper for more details about the others. We show that any code similarity scheme can be extended to a search as well as clustering schemes. This is why we focus our attention on the evaluation of our similarity function, while we aim to improve search and clustering schemes. In the context of malware principles, we also propose the accuracy and robustness paradigm. This idea is motivated by the work on challenges in evaluating malware clustering published in RAID Conference 2010. The authors revisited an existing work that had achieved high F scores in their clustering evaluation. Without changing anything in the clustering algorithm, nor in the source of the labels used as ground truth, they repeated the experiment with a new dataset, and this time the F score obtained were much lower. The authors conjectured that the differences in the F score are related to the difficulty of the datasets, which is intrinsically connected to the way that each dataset was built. They leave as open problem the elaboration of a methodology that takes into account this issue. We propose the accuracy and robustness paradigm as a two-phased experiment where one phase assesses the accuracy of a scheme and the other its robustness. The accuracy phase is performed on a dataset that is, by construction, easy to evaluate and rely on external validity, such as the measurement of the F-score with respect to some external ground truth. To build this dataset, it's necessary to follow some stringent methodology, such as labeling consensus with different tools or sources, as in the work presented in the previous slide, or labeling through some very specific string matching, such as proposed by Florian Roth as part of the YARGEN tool. In its turn, the robustness phase takes a dataset representative of the real world and evaluates how the score measured degrades as cleanware is inserted to function as noise. In this case, we are mostly interested in internal validity. Now we present ECDGs and how they are obtained. To build ECDGs, we perform symbolic execution of malware samples and we inspect all calls made between the main binary object of our target file and the system or any shared object, also called shared library, hence the name external calls. And we observe the interdependencies of these external calls. For instance, we see in the right hand side 3 calls: open, read, and write. We can see that the open function returns a handle that is passed to the read function and later to the write function. The read function returns a buffer that is passed to the write function. All these variables are connecting these functions together, and we draw them as edges in our graph. Hence the name dependency graphs. They are ideal to capture data flow dependencies. Furthermore, they are compact since they don't include implementation details, as for example control flow graphs do. And they are also resistant to code mutations that rely solely on syntactical properties such as instruction replacement, opaque predicates, etc. We define our pairwise similarity function as shown in this slide. We see that it depends on a value alpha that we name node edge factor or NEF. Given two graphs, the NEF value will balance between similarity found with respect to their nodes or with respect to their edges. In its turn, the node similarity is computed by counting how many nodes are found in common between the two graphs divided by the lowest number of nodes in the input graphs. And the edge similarity counts the number of edges of the largest connected component in the biggest common subgraph divided by the lowest number of edges in the largest connected components of the input graphs. Here we see how the evaluation framework was mounted. We first extract the calls using symbolic analysis, then we generate the ECDGs to finally compute the similarity between them. For evaluation purpose, we compute clustering based on our similarity function. The goal is to evaluate the clusterings with different algorithms and to compute external and internal metrics in these clusterings. Our evaluation dataset is present in this table. We have 3 classes of files. Class 1 is composed of files matched with rare strings, or more specifically the VSSM methodology as discussed before. Class 2 is composed of files matched with YARA rules from public repositories, being representatives of the real world. And Class 3 are cleanware samples. In this slide, we see the results of the benchmark comparing our similarity function with HADIF2, an open source tool from the HADAR tool suite that computes binary code similarity. We see that our similarity function achieves a speedup rate of 3.3 times with respect to HADIF2, and with a cache-enhanced implementation where call traces are kept in the cache, this speedup reaches over 350,000 times. These measurements took into account over 175,000 pairwise computations with files of our class 1 samples. We also measure the results of these pairwise computations. For these, we define 4 categories: the strong dissimilarity for values between 0 and 0.25, weak dissimilarity for values between 0.25 and 0.5, weak similarity for values between 0.5 and 0.75, and finally, strong similarity for values between 0.75 and 1. The table maps the pairwise computations that HADIF puts in the same category with respect to the category that our similarity function found for the same pair of files. Each cell contains the percentage of files in this mapping. Ideally, if HADIF and our similarity function were equivalent, we would find values only in the skew diagonal. However, we see that we are able to find strong similarities where HADIF finds weaker similarities or even dissimilarities. As we saw, our similarity function requires the definition of the NEF value. Therefore, to select the NEF, we do an exploration varying the values from 0 to 1 in steps of 0.05, and we use the class 1 files in our dataset, since we aim for maximum accuracy when picking the NF value. Then the exploration goes as follows. For a given value of NF, we compute the similarity matrix with all possible pairs of files. We compute the clustering using multiple algorithms, and for each algorithm we compute different metrics. Here we see one of the curve profiles that we obtained in this exploration. It shows the metrics for different values of NF using HDBScan. We choose this profile to guide our selection for the NF value because HDBScan provided the best results overall. Furthermore, we decided to pick homogeneity as our main metric, which fixed the value of 0.25 for the NF. We then follow the accuracy and robustness paradigm in our evaluation. Here is the result for the accuracy phase. We see that overall, we were able to achieve high homogeneity scores with different clustering algorithms, which means that the ECDGs are as accurate as manually crafted IRIA rules that match rare strings to discriminate the malware families. We also see the heat map in which the pair of files that are not similar are marked with darker points in the map, whereas similar files are marked with lighter points. The points were sorted with respect to the output of HDBScan. Therefore, in this experiment, we can say that ECDGs can autonomously provide results that are as accurate as manually crafted. Here we can see the results of the robustness phase. The initial clustering contains only class 2 files, and we see that different from the accuracy phase, the families are not necessarily very distinguished from one another. One of the reasons relates to the poor quality of IRIA rules. For instance, we found a rule for the emotet family whose description was a pruned aggregate of all emotet related strings extracted from clam AV on a certain date. The final clustering was computed with all class 2 files and also with the cleanware samples. We can see that most of the noise was not included in the initial clustering. Even by eye, it's possible to retrieve the initial clustering profile within the heat map of the final clustering. The normalized mutual information measured between the initial and final clustering was 0.974, meaning that the information loss due to the insertion of noise was only marginal. This slide shows the curve profile for the robustness phase. We see that the homogeneity score slightly increases with the insertion of noise. The silhouette score is the most affected metric as it is impacted by new rather small spurious clusters, and that the other metrics do not degrade a lot with the noise. This shows that our similarity function based on ECDGs is robust. We also investigated the possibility of computing clustering prototypes, which is defined as a data object that is representative of the objects in a cluster. For this, we define the prototype as a common subgraph of the graphs in a cluster. Here is one such example of the Wabot family obtained in the robustness phase. To conclude, we define ECDG as a call graph to optimize the representation of argument dependencies between calls. That allows more concise structural representation of programs with no loss of information. We propose a new similarity function that is efficient and was evaluated according to the accuracy and robustness paradigm. The accuracy phase produced almost unary results with homogeneity score of 0.983, which shows that our evaluation framework manages to autonomously describe malware families that are as accurately as a set of strict handcrafted IRIA rules. The robustness phase verified that the clustering was robust to noise insertion, having almost no impact on homogeneity and mean similarity, and only mild effect on completeness and silhouette score due to the creation of many singletons. The normalized mutual information score between the initial and final clustering of this phase was 0.974, indicating that the information loss due to the noise insertion was only marginal. The main limitations of this study are the use of symbolic execution and the scalability of our evaluation framework. As well known, symbolic execution is not optimal to analyze packed samples. We tested the ARES option to enable self-modifying code support, but we did not notice any major gain. Furthermore, symbolic execution is very resource intensive, notably when it comes to the memory. Indeed, 96% of our analyses were terminated due to memory exhaustion. With respect to the evaluation framework, since we intended to compute clusters with different algorithms, we decided to rely on similarity matrix. However, the computation cost to compute them is n squared. Therefore, we had to limit our evaluation dataset to a few hundreds of samples. This is it. Thank you.